Now, students, let us take the economic order quantity further. Let us check it in a multi-period scenario. So in multi-period, you would have more than one period. Just remember that economic order quantity is a single period model. It's the inventory model that is applicable for a single horizon. And you assume that every horizon is actually the same. But your inventory levels could differ. It could vary from one period to another period. It might be possible that your demand varies in every period. And if it is the case, then every horizon or every time period of your demand would not be the same. Units would vary, and you cannot just use a simple EOQ, which is like more applicable for the same type of inventory periods. So in that case, we need to formulate a constraint problem that would be essentially like a linear programming model. When I say it's a linear programming model, you should know that there would be constraints that need to be satisfied, and under those constraints, we would be minimizing the total cost function. So how would it look like? Let me first introduce you to some of the notations that I would use for my multi-period inventory model. Let's XT is the quantity ordered and received in period T. The lead time is assumed to be 0. You assume that you have received some quantity in some period T. So period T would become a subscript of X, and you don't know what is the quantity ordered. Your quantity order would actually change in every period because you would have some inventory with you from the previous season, and you will adjust it in the next season as well because your demand would vary in every period. That is the main assumption here. I naught, the inventory at the beginning of the planning horizon. So when you are using this model, you will have to start from somewhere. So I naught would represent the inventory at the start of the planning horizon. IT would actually represent the inventory at the end of period T. So I naught at the start of the season. IT, the inventory position at the end of the season. Then we have IN, is the desired inventory, ending inventory. You would like to have some inventory with you. That desired inventory would be IN. Then CT is the purchase price in period T. Here we can assume that our price change, the cost price would be significantly different or different in every season or every period. So it would be represented by CT. Then we have big T with the subscript T, which is representing the time period here, is the cost of transportation in period T. Then HT, holding cost in period T, including interest and storage cost. It can differ from period. That means it might be possible that my holding cost in period T minus 1 would be different from the holding cost in period T, or which could be different from period T plus 1. Then DT is the demand in period T. It could differ as well. That means I can have like different Ds in these periods. Then ST is the availability of supply in time period T, and VST is the storage capacity. That would be the total storage capacity for. So using these notations, this would be my multi-period inventory problem, which is actually like a linear programming model. I can solve it with the help of a linear program, standardized or generic linear program if it is as simple as this one. What I have a minimize Z function, which would be the sum of all the periods XT, CT plus T. XT is the inventory position in any time period T. So you will sum up what you will do. Let's say I have some inventory X for period 5. I will multiply it with C5 plus the transportation cost in that CTT plus the sum of ending inventories IT into the holding cost in some time period T. IT, remember, it was the ending inventory in any time period. I would like to minimize this objective function with subject to following constraints. My XT, that means the inventory which I have ordered or I have received in a time period, plus the inventory from the previous, ending inventory from the previous period. If XT is like, let's say 5, so it would be I4. The ending inventory at the 4th period should be less than or equal to my total storage capacity. VST actually represented your total storage capacity. For all T, for every time period, for all time period T. Then my second constraint would be my ending inventory of the previous period, ID minus 1, plus the inventory which I have purchased in the current time period, XT, minus the demand of the current time period, should be equal to my overall inventory, ending inventory in that time period, overall inventory in that time period for all T. Then I need to satisfy that XT is actually less than my storage cost. That means my storage, jo units are rahe, the units which I have, again, they are less than the storage which I have or equal to. And then we have the non-negativity constraint as usual, which you do for linear programs. Non-negativity constraints are there. That means IT and XT should be greater than equal to 0 for all T's. Now students, the first term on the right hand side represents the sum of purchase cost and the transportation cost. I explained that. The second term of the objective function actually represents the total holding cost incurred. The constraints then include the storage capacity, restrictions, and inventory balance constraints. So the first constraint which we had actually ensures that the maximum inventory level does not exceed the available storage capacity. The second constraint indicates that the inventory at the end of the period T is given by the inventory at the end of period T minus 1 plus the quantity received in period T minus the quantity consumed in period T. So, एक आपके पास ending inventory है plus what you have purchased minus what you have consumed, that is the demand for that time period. The assumption here is to meet the demand in every period without any shortages. That means whatever inventory you had, whatever you purchased, whatever is consumed, it should be actually equal to your demand, actually equal to your inventory. Equal इसलिए था, you want to ensure that the inventory which you have actually satisfy the whole demand without any shortages. The third constraint limits the order quantity to the available supply. Supply थी storage जितनी आप कर सकते हैं उसकी, तो S को supply जितने मेरे पास है capacity, जितनी supply मुझे चाहिए उस हिसाब से I should have the available inventory with me. The final constraint actually represents the non-negativity of the decision variables. So this was actually one of the simple multi-period inventory models. If you can recurse it, it wouldn't be easy because from one horizon to next horizon you have to move. So it actually becomes dynamic in nature because your I would be changing, your inventory levels would be changing, your demand would be changing. So it actually becomes a dynamic program. But fortunately, these simpler programs can be handled by the softwares which incorporate linear programming and dynamic programming. So they can recurse it, and you just need to actually have different values with you, and you can actually get the result for it as well. So it's not like that you have to do it by hand, or you have to calculate, you have to solve this problem by hand. It can be, we have information systems with us, we have softwares with us, off-the-shelf softwares, generic softwares, which can actually solve these type of problems as well. So it's not that tough, but you should know the basic understanding of a multi-period, that inventory levels could change dynamically, and if they change, then how can you get your inventory levels or your quantity to be ordered in every period. Thank you.